किया था उन लोगों ने, इंदौर के एक कॉलेज
मीट में कर रहे हैं तो सभी में कर सकते हैं, जूम कंपेयर टू गूगल मीट। अच्छा,
नहीं मैं गूगल मीट से ही किया ज्यादातर, ये अभी पहली बार देख रहा हूँ मैं जूम वाला।
जूम का
हाँ,
जूम सबसे सिंपल जूम है सर।
हाँ वो बोलते हैं, लेकिन हमने मैं क्या क्लासेस जो ले रहे हैं ना, हम वो गूगल मीट से ही ले रहे हैं, ऑनलाइन क्लासेस।
ओके ओके ओके, आपका ऑनलाइन क्लास अभी भी कॉलेज स्टार्ट नहीं हुआ सर?
नहीं नहीं हुआ हमारे यहाँ। तुम्हारे यहाँ हो गया क्या?
हो गया सर, अभी 3rd ईयर 4th ईयर को ऑफलाइन क्लासेस है, फर्स्ट ईयर 2nd ईयर को ऑनलाइन क्लासेस है।
अरे यार हमारे यहाँ नहीं हुआ यार, हमारे यहाँ मतलब एग्जाम होंगे अभी बस, उसके बाद देखेंगे फरवरी में।
ओके, अभी फर्स्ट मिड चल रहा है 3rd ईयर 4th ईयर को, वो होने के बाद फिर फर्स्ट ईयर 2nd ईयर आ जाएगा, 3rd ईयर 4th ईयर को ऑनलाइन चलेगा
ऐसा। अच्छा, नहीं हमारे यहाँ तो अभी ओपन नहीं है।
हॉस्टल में सोशल डिस्टेंस मेंटेन के लिए।
अब वो हॉस्टल में तो कहाँ सोशल डिस्टेंसिंग होगी।
Okay, sir, we'll start.
Okay.
So, good morning to Manoj Kumar Gupta, sir, and dear participants. I welcome you all for the today's faculty development program on renewable energy intervention in industry, domestic, and commercial applications. So, today we have with us Manoj Kumar Gupta, sir. He is going to deliver an expert talk on exergetic analysis of solar air heater and water heater. And I think before starting the session, I request Professor V. Sivardi sir to introduce the today's expert.
Okay, thank you, sir. You are given great privilege for me because my guru host, we can call anything, Gupta ji. Dr. Manoj Gupta ji is a professor and head Ujjaini Engineering College, Ujjaini Government College. That professor and are secondary. He is a top bearer for my life, especially. Why? Because when I joined PhD in IIT, I am doing coursework. I don't know what to do, how to complete, how to start research also I don't know. I am searching refrigeration, I am searching power plants and all. In QAP program, for attending, he came to Delhi. Then he given his thesis, that's all. The end chapter of Gupta ji is my starting chapter of my thesis. And also, not only just giving thesis, he guided how to calculate the overall heat loss coefficient of receiver. That is part of my entire thesis. Total code also he given. That's why in my life, Gupta ji, Manoj Gupta ji, one of the torch bearer, no doubt at all. Ranjan ji, Pawar ji is the supporters for me to successful completion of number of papers. But start of my PhD, how to execute, because within 2.5 years I completed my PhD because of his experience only. So it is great privilege. Okay, he's a professor and HOD, and he wrote one textbook on power plants. I think in Madhya Pradesh, majority of the BTech student, BTech mechanical is following the textbook compared to PK Nag. So very good textbook, and he published more than 20 publications. Out of that, majority of the publication highest cited. Why? Because general research publications citation is very less, but his citations more than 80, 90 citation is there. You can cross verify Manoj Kumar Gupta ji. So it is means whatever the work he did, he is a torch bearer of other researchers also. Just I published paper, not like that. And also is one kind of mentality. I'm not saying because before joining IIT Delhi, I don't know the Manoj Gupta sir, and he also don't know about me. But he supported a lot. So entire life my gratitude goes to sir, because for any person excellence who are supporting, we have to show the gratitude. Then only they can support other persons also. Otherwise, they will stop supporting. That's all. So it's a great privilege, sir. With this small introduction, I'm giving session to you, sir. Now session is yours. Up to 12:30. Yes, sir.
Thank you, Siva Reddy, for your kind words. Actually, you have also helped me a lot during my PhD thesis. So thanks you. Good morning to all. Am I audible?
Yes.
Yes, sir. Yes, sir. You are
Yes,
right.
sir. So today I will deliver, or my lecture will be based on energy and exergy analysis of solar thermal collectors. The topic of your FDP program is very good. Renewable energy intervention in industry, commercial and domestic applications. Now, before starting about the exergy analysis of solar thermal collectors, I will discuss. Let me begin about energy. All of we know energy is the backbone of human activity in all sectors of life, and the demand of energy is increasing day by day because of growing population and development in various sectors. And we know the major energy hello majority of our energy demand is provided by the consumption of fossil fuels. And as we know, these fossil fuels, coal, oil, and gas will not last longer. It is said that coal will be available only for next 200 years, oil less than 50 years, gas less than 25 years. That's just estimation. But the consumption of these fuels also have negative impact on our environment. So for sustainable development as well as to protect the environment, it is necessary to use the renewable energy sources. So that's why I have told the topic of this FDP is relevant in present scenario, because we are facing shortage of primary energy sources, or these fossil fuels. So we must switch, or we must use, or promote the use of renewable energy sources for sustainable development. And the solar energy is one of such kind of renewable energy source. It is said that if we can trap, as all of you might know, that energy is generated inside the sun due to conversion of hydrogen into helium, continuous conversion of hydrogen into helium, that is nuclear fusion reaction. The temperature inside the sun is very large, but at the surface of the sun it is estimated to be about 5600 Kelvin. So sun radiates heat energy as per Stephen Boltzmann law, and the radiation also reaches on the ground. And it is said if we can trap only 5% of this energy received from the sun on the ground, then we can meet the entire energy consumption demand of the world. So that's why solar energy is a very large source of energy. Definitely it is renewable, and it is very, very large. Now, energy from the sun we can utilize by using solar cell or by using solar thermal collectors. Indirectly, we are using solar energy since long. That's why we treat the sun as God, because sun provides the energy in various forms. For example, biomass, photosynthesis reaction is in the presence of sunlight. So the biomass, or energy from biomass, is an indirect form of solar energy. So let me focus on direct conversion, either using solar cell or solar thermal collectors. So today's discussion will be on solar thermal collectors. Solar thermal collector is nothing but a heat exchanger. Solar collectors are a special kind of heat exchanger that transform solar radiation energy to heat energy to some transport medium. Now, the principle of collection of any solar thermal device is, first, assume a black absorber surface. Black or absorber surface having high absorptivity. Now, the absorber surface may be a flat plate, maybe in the form of a tube, or maybe in the form of cavity. First, there is an absorber surface whose absorptivity is very, very high for solar radiation. Now, radiation falling on that absorber surface is absorbed. Due to absorption of solar radiation, the temperature of absorber or receiver surface increases. So now the heat energy of this absorber surface is transferred to some transport medium for some useful heat gain, depending on the type of collector. If it is a water heater, solar water heater, then heat energy is transferred to the water. If it is air heater, then transferred to air. If it is a heat transfer fluid, then energy is transferred to the thermic fluid or heat transfer fluid. In case of solar cooker, heat energy is transported to the items to be cooked. So principle of collection of any solar thermal collection device is simple. First, there is a black absorber surface. Solar radiation falling on the absorber surface is absorbed by the absorber surface. Temperature of surface rises, and then the heat energy is transferred to the transport medium for useful heat gain. As the temperature of absorber surface rises, means the temperature becomes different than surrounding temperature. So definitely heat loss will also take place from the absorber surface to the surrounding by radiation convection. So in order to prevent the heat loss, in all of the solar thermal collector, absorber surface is surrounded by a transparent cover or a glass cover. And the purpose of glass cover is to reduce the heat loss by convection and radiation from the absorber surface towards surrounding. How? Because by providing glass cover, but the direct contact of surrounding air is prevented. So now heat loss from the absorber surface, which was taking place directly from absorber surface to the surrounding, will now take place first from absorber to the glass by convection and radiation, within glass by conduction, and then from the top of the glass by convection and radiation. So by putting glass, the heat loss by convection and radiation reduces. There is one more property of the glass. Glass is transparent for incoming short wavelength solar radiation. Or actually glass is transparent for our visible or short wavelength radiation, but glass is opaque for long wavelength radiation. As per the Wien's displacement law from the heat transfer, we know lambda mt is equal to 0.29 centimeter Kelvin. So actually everybody emits the radiation from 0 to infinite wavelength. So sun also emits from 0 to infinity, but major power concentration in solar radiation in short wavelength region. So we assume, or we say, short solar radiations are of essentially short wavelength in nature, while radiation emitted by absorber surface are long wavelength. So the glass allows the solar radiation to come in, but it blocks or it acts as opaque material for radiation emitted by the absorber surface. So by putting glass cover, we reduce the heat loss. Now, solar collectors, now this is the principle, are classified as flat plate collector and concentrating collector. All of you might have seen the box type solar cooker. In box type solar cooker, a mirror is provided on the lid of the box. The mirror is provided on the lid of the box. If we remove that lid, then that solar cooker without the mirror is a flat plate collector. But if we use that mirror, then it becomes concentrating, because we are using some concentration, or we are concentrating solar radiation falling on a reflector or refractor towards the absorber area. So in case of flat plate collector, there is no optical concentration, but in concentrating collector, we use reflector, mirror, or refractor, or lens. And definitely in concentrating, what we are doing, we are concentrating radiation falling on large area to a very small area. So definitely temperature attained by the collectors, concentrating collector will be more. So first we classify as flat plate and concentrating, and then concentrating may be further classified as non-imaging, imaging. Means whether image is formed. I think all of you might have burned a paper by using lens. So what we do in that, we focus is around at a point. So concentrating collector based on focus may be point focusing type or line focusing type. Now there are various applications of solar thermal collectors. For example, water heater to heat the water, solar air heater to heat the air, and others applications. So I will come to the analysis of solar water heater and solar air heater, especially these later. Now, just proceeding further, we can see these diagrams. This one, if you are seeing, this is the solar cooker, which I have told this on the lid, there is mirror. This lid position can be adjusted. Adjustable mirror means inclination can be changed. Now this diagram is conventional liquid flat plate collector. And in conventional liquid flat plate collector, there is a flat. I am talking about conventional because nowadays the solar water heater for domestic application is evacuated tube type. This is conventional, in which there is a absorber plate, and at the back of the absorber plate, number of tubes are welded, soldered, or clamped to the absorber plate, and these tubes are connected to the header tubes. So water flows towards this tube and being heated and collected in the storage tank. On the next diagram is for solar air heater. Whenever there is a flow of air from the fluid mechanics, flow of air is always through the duct in order to keep the pressure drop within limit. As we know from the Darcy Which-Batch equation, 4 FLV square upon 2 GD. In case of gas flow, for given mass flow rate, volumetric flow rate is high. So if the compressible fluid or a gas is made to pass through a smaller cross-sectional area passes, then pressure drop will be more. So in order to keep the pressure drop within limit, the flow of air is always through a duct. Instead of pipeline, we use duct, and in case of solar air heater, duct is formed by, first there is absorber plate, then a bottom plate, absorber plate and bottom plate, and the space between the absorber plate and bottom plate forms a duct. So air flows through the duct in case of air heater. Now this is the concentrating collector. In this we use, this is the parabolic trough collector. We use first there is a cylindrical parabolic reflector. Reflector is in the form of cylindrical parabola. This profile is parabola, and receiver tube or absorber tube is placed at the focus, surrounded by a glass tube just to prevent the heat loss by convection and radiation. And now if we are using concentrating collector, then we can also use selective coating, and second we can create the vacuum in the annular space between glass tube and absorber tube. In case of this flat plate collector, suppose this solar cooker, we cannot create the vacuum between flat glass and inside of the box or this cooker, because glass is breakable. We cannot create vacuum in this. But in case of concentrating collector, the vacuum can be created in the annular space between absorber tube and surrounding glass tube. And definitely if we create the vacuum, then convection heat transfer is further reduced. So by creating vacuum, we reduce the convective heat transfer, heat transfer due to convection from this absorber towards the glass tube. Because here area of the absorber surface or receiver tube is small, so we can go for selective coating. H per heat transfer, you might have studied about Kirchhoff's law, which says absorptivity is equal to emissivity. Now this absorptivity may be on the total basis or based on particular wavelength. So Kirchhoff's law says monochromatic emissivity is equal to monochromatic absorptivity. Means emissivity for a wavelength is equal to absorptivity for that wavelength. Similarly, total emissivity is also equal to total absorptivity. Now everybody emits radiation of all wavelength. As I told, solar radiations are of short wavelength in nature. So it may be possible to, or there are some coatings which has high value of absorptivity or emissivity for incoming solar radiation and low value of absorptivity or emissivity for outgoing radiation. So if we use the selective coating, then what will happen? The radiation is absorbed as much as possible. But when for the re-radiation, because the emissivity is less, so amount radiated will be less, or definitely we can reduce the heat transfer by radiation. So in case of concentrating collector, we have the provision for evacuation as well as to use the selective coating. Now I will come to especially my points. Exergy. Before exergy is capacity, exergy of any form of energy is the maximum work that we can derive from that energy. For example, potential energy. Water is stored at high altitude. Then that potential energy of water, as we know from hydraulics, can be converted fully, if we ignore the friction, into work or any other form of energy, because potential energy is high grade energy. But heat or thermal energy or internal energy, etc., are low grade energy, and complete conversion of low grade energy, especially heat energy, is not feasible into high grade energy. For example, if we have heat Q from a source at temperature T, heat Q from a source at temperature T. Source means if we extract the heat Q from that source which is at temperature T, the temperature of source will not going to change. Now we can utilize this heat Q in a reversed heat engine cycle or Carnot cycle to develop the work. And work developed will be heat supplied into efficiency of heat engine. And efficiency of heat engine is 1 minus T rejection upon T heat addition. Means in this manner we can calculate the useful work that can be obtained from heat energy. So the exergy or the second law of thermodynamics, actually first law deals about the energy, while the second law talks about the quality of energy. Or logically we can say heat energy at 30 degrees centigrade and heat energy at 200 degrees centigrade. So definitely heat energy available at 200 degrees centigrade is better than that is available at 30 degrees centigrade, because near heat energy available at near ambient temperature is of no use for us, but we can use, or the exergetic value of heat energy available at higher temperature is more. So for energy conservation of point of view, we should include the exergy analysis, or we should talk in terms of exergy besides the energy, because definitely we will have to use the energy balance first. So the exergy concept based on second law of thermodynamics provides insight into optimum means of using energy to perform a given task. Let me skip it. Now come to why this your FDP topic is relevant to this exergy analysis. Currently, much heat from fossil fuels with high availability level is used for applications at 300 degrees centigrade or below. For example, to heat the water for bathing purpose, we normally use electric geyser. Means we are using high grade energy, electric energy, just to heat the water at 80 degrees centigrade. Means currently much heat from high grade energy sources are used for applications at 300 degrees centigrade or below, which can be obtained by using variety of solar thermal collection devices. For example, water heating. Instead of electric geyser, we can use solar water heater. So actually there is a degradation of energy by using electric geyser. I will come to those points later. Now the most promising areas are those which are high entropy task. Means where we can use renewable or solar energy instead of using high grade energy for low temperature applications. And the low temperature application may be space heating, space cooling, water heating. Actually, space cooling means by using heat energy in vapor absorption refrigeration system, in either ammonia water system or lithium bromide water system, water heating. All these are the applications where heat energy is required at low temperature. I have not mentioned power generation. And these low temperature heat requirement can be fulfilled by solar thermal energy. And if we promote the use of solar thermal energy in such, then we can conserve our exergy rich fuel. Now the various, because your topic is in industry, and so there are various sectors where heat is required at low temperature. In food and textile sectors, temperature levels required are so low that the demand can very easily be supplied by solar energy. For example, the hot water requirement for soaping, washing, boiler feed, dyeing machines, air, and low temperature process can be provided by selectively coated FPSC. Now, actually, we were discussing that below 300, there are various applications where temperature is required below 300 degrees centigrade, and that temperature can be obtained by using variety of solar thermal collectors. Again, this solar air heater can be used for drying of yarn in various textile and other industry. Parabolic trough collector may be used to produce the low pressure steam, and that can be used for other purpose. Even in case of thermal power plant also. Now, if you go this point, I think Siva Reddy might have discussed it. Dr. Siva Reddy might have discussed. In case of solar thermal power plant, the steam leaving the turbine is condensed in the condenser, and the temperature of condensate is leaving the condenser maybe 60 degrees centigrade, about this. While the steam is generated in the boiler at about 540 degrees centigrade or maybe more. I am talking about the steam turbine based power plant. Now this water leaving the condenser is supplied to the boiler through various number of feed water heaters, again to reduce the exergy loss in the boiler. So the water is reversibly heated in various number of feed water heaters from condenser temperature to the entry temperature of the boiler. But still in the boiler, the water supplied is first heated up to saturation temperature, and then steam generation takes place. Now, by using solar energy, what we can do, we can further heat the water leaving the high pressure feed water heater. Suppose last feed water heater, and then this water is further preheated by using solar thermal energy. So in this manner, we can reduce the irreversibility in boiler, or what we can do, we can utilize the exergy rich fuel, or if the flue gas temperature is at let us say 1000 degrees centigrade. So we will not use this flue gas which is available at 1000 degrees centigrade to heat the water at 250 degrees centigrade. What we will do, we will use this heat energy to generate the steam at 300 degrees centigrade or more, provided the heating of feed water is carried out by using solar thermal energy besides feed water heater. So there are various options to use the solar energy, low temperature, as well as, because by using concentrating collector, we can generate temperature more than 1000 degrees centigrade. So solar energy can be used even to create a furnace. Now, again, this first law. In first law, we write, first law is based on law of conservation of energy. Energy in is equal to energy out. Energy entering is equal to energy leaving. And while writing the first law of thermodynamics, what we write? Energy entering associated with mass transfer or flow stream, that is kinetic, potential, and internal energy. Then, and energy associated with heat transfer, there are entering energy group. While in energy group, leaving energy group, we write again energy associated with mass transfer, that is energy leaving the group along with the matter, plus energy transferred due to work developed by the system. This is the first law of thermodynamics for open system. Now, in this, energy associated with steady stream of matter comprises of kinetic energy, potential energy, and internal energy. This relation I have mentioned because exergy is the maximum work that can be produced from the given form of energy. So I have discussed, if we are having heat Q from a source which is at temperature T, then by using a reverse heat engine or Carnot cycle, the maximum work that can be developed is Q multiplied by this term. That is the exergy associated with heat transfer. Means if heat transfer Q takes place from a source at temperature T, then its exergy value is Q multiplied by this term, similar to the efficiency of Carnot or reverse heat engine cycle. So we can calculate the exergy of heat transfer. So definitely, if the temperature of heat source is high, its exergetic value will be high. So heat energy available at 100 degrees centigrade and at another heat available at 1000 degrees centigrade. So definitely exergy value of heat energy available at 1000 degrees centigrade will be more, or we can develop more work by using heat available at higher temperature. Now, energy associated with stream, kinetic, potential are high grade energy. Means exergy value is equal to itself same, but physical specific exergy depends on initial state of matter, and we calculate its enthalpy minus ambient temperature into entropy, H minus TS. Now, in comparison to first law of thermodynamics, energy in equal to energy out, the exergy balance is written in this manner. Exergy in is not equal to exergy out. As per first law, energy is always conserved. But as per this extension of second law, exergy is not conserved. And we should try to conserve the exergy, or we should try to judiciously use the energy so that we can conserve the exergy, and exergy balance is exergy in is equal to exergy out plus exergy loss. So if we compare with first law, then this exergy in associated with flow stream, and in case of Q, exergy associated with heat transfer. This EXW, exergy associated with work transfer. Now work means high grade energy. So this exergy associated with work transfer is equal to work itself plus IR, where IR is irreversibility or exergy loss. And exergy loss is calculated by this Stodola theorem, T as generation, and this as generation is calculated by using this. Now I will come to this first law efficiency and second law efficiency. Now efficiency term we define output upon input. That is, if we use energy in both numerator and denominator, then it is first law efficiency that we commonly use. But if we use exergetic value instead of energy, then it becomes second law efficiency. All of we study in about in refrigeration, air conditioning. The performance of any refrigerator is output upon input. Output is desired effect, maybe heating or cooling. Input is work. And for the most of the refrigerating system or cycle, this terms comes out to be greater than unity. But refrigerating effect upon work input. Why it is more than one? Because we are using high grade energy to create the produce the refrigerating effect. And that's why there in refrigeration we never use efficiency term. We use coefficient of performance, because this ratio comes out to be more than one, means this first law efficiency may come out to be more than one for some application. That's why we use COP term in refrigerators. So more appropriate is to use this second law efficiency. How? We will discuss it if it is feasible. Now this example, all of you, especially those who have studied the thermodynamics, might have solved this problem. Let us illustrate the second law efficiency of a gas heating system designed to maintain building at TU. Suppose I want to maintain the space, a confined space at TU by using flue gas. So what I can do? Burn the fuel and supply the flue through the duct or pipe towards the space. So if heat Q is added to building at temperature TU by using heat QF from the flue gas. If it is not clear, then again take the example of electric geyser. In electric geyser, by using 1 kilowatt electricity, or for 1 unit 1 kilowatt hour consumption, suppose by using 1 unit of electricity consumption, and in case of electric geyser, what we can say? It is perfectly insulated. So all amount of electric heating is transferred to the water, or that electricity is utilized, completely utilized to heat the water. And if we assume some losses, even then efficiency is close to unity. In case of electric geyser, output upon input, whole electricity is utilized to heat the water. So first law efficiency is nearer to the 1, or it may be 100% or slightly less than 1 in case of electric geyser. So based on this first law or only energy consideration, what we can say? Electric geyser are highly efficient because they completely convert electric energy into heat energy. But can we convert that heat energy into electric energy? Obviously, answer is no. So we must think from the available energy point. So it's the same example. If the heat Q is added to building at utilization temperature T, then using available energy concept. Suppose I have added heat QU at temperature TU, then its exergy value is again from that relation Q multiplied by the efficiency term. So minimum exergy input required to add the heat Q at TU. Suppose I want to heat the space at TU, then what I can do? One option is use some heat transfer fluid or air or flue gas, which is at temperature nearer to the temperature to be maintained in the room. One provision is this. Another is I can use air at 1000 degrees centigrade. So again, definitely our aim is only to heat the building at maintain the temperature TU by adding heat QU. So available energy is this much. But if this heating is carried out by using heat QF at temperature TF, then available energy which we are using to perform this task will be A, this much. So second law efficiency, again in nutshell, I want to heat the space at temperature TU by adding heat QU. So my desired output is QU in terms of energy, while in terms of exergy or available energy, output is, what is its exergy value? Exergy value is this much. And this task is performed by using heat QF at temperature TF. So in terms of energy, I am adding heat QF. While in terms of exergy input is this much. So the second law efficiency, all of you might have solved this example like this. And same, either electric geyser example or this. The first law efficiency is close to the unity. But the second law efficiency from this example, if I take the fuel temperature, source temperature to be 2300 Kelvin, then the second law efficiency is only 0.0515. Basically what we are doing, we are using exergy rich fuel source or heat energy available at a very high temperature to heat the space at very low temperature. So the second law efficiency is very low, or there will be large entropy generation, or there will be much irreversibility. So actually we should try to use the solar energy for such low temperature application, and in this manner what we can do, we can conserve the heat energy or fuel sources. For example, if I want to heat the water at 60 degrees centigrade, why should I use electric energy? All of us should use or promote the use of solar energy for the low temperature applications. Especially if we are using electric motor, then definitely you will have to use the electricity. But the geyser, as per the thermodynamics, second law analysis, geyser is not an efficient device because we are converting high grade energy into low grade energy. So for such low temperature application from the second law, but conclusion is we must use the either waste heat energy sources or solar energy or other energy sources available at low temperature to preserve the exergy rich fuel. Again, all of you might have solved one more example, or let me take from this example of refrigeration. Suppose I want to heat a room and I want to heat 1 kilowatt hour or 3600 joule heat to a room. And this heat I can add by using a electric heater by the consumption of 1 unit, 1 kilowatt hour. So to add 3600 joule heat, I have consumed 1 unit of electricity. Now think, if I use this 1 unit of electricity in a heat pump, reverse of refrigerator, and if as we know, COP of heat pump is always more than 1, and suppose the heat pump is based on vapor compression cycle, so if we take COP is, let's 3, COP value is equal to 3, then what I can say, by using that 1 kilowatt of electricity in a heat pump, I can add 3 times heat to the room, or I can say, just to add that 3600 joule heat, I will require 1/3 of the power input in comparison to direct heating. So you can see I think this exergy point will be clear to most of you. Now the solar energy, again I am again and again repeating that we should use solar energy. Actually, solar energy is also exergy rich, because by using same solar radiation, we can create the temperature about up to 100 degrees centigrade in flat plate collector, up to 400 degrees centigrade in case of parabolic trough collector, and more than 400 or up to 1000 in paraboloidal dish. It means the same solar radiation we can create the temperature, different temperature depending on the collector. So the solar energy is also exergy rich. But what will happen if we do not use the solar collectors? What will happen? Solar radiation will be dissipated everywhere. Thus, solar collectors should be used with an aim to maximize exergy output delivered by the collector or exergy gain by the fluid transport medium due to its cost effectiveness in spite of low exergy output. Now, let me come to my topic. Exergy analysis of flat plate solar collector for water heating. Conventional. These are some relations which I will discuss. This relation is solar radiation falling on a glass cover, on the top of the glass cover of a flat plate solar collector. And in this relation, tau, this subscript B stands for beam radiation, D for diffuse radiation. Tau is the transmissivity of the glass. Beta is the slope of the collector. As you might have seen, the solar flat plate collector is normally inclined at certain angle and facing due south. Is placed south facing and inclined at some angle from the ground. And that angle is dependent on the latitude of the location, plus minus 10 degree. And depending on if we are using in winter, then the inclination may be more. And if its use is more during summer, then inclination will be less than latitude. So beta is the slope of the collector. IB and ID are for beam and diffuse radiation. And this θ1 is angle made by solar radiation with normal to the collecting surface. And again, I will not come to these relations. Just I am giving the idea that the radiation falling on the absorber surface or any collecting surface, maybe our building itself, the solar radiation intercepted by the roof will be different than by walls at a particular instant. And in the wall, we can say radiation falling on south wall will be different than east wall. So radiation falling on a collecting surface depends on various parameters. So this angle theta is angle made by solar radiation with normal to the collecting surface, and which you can observe during the morning hours. Solar radiation we can see apparent coming from the east, from the during noon we can observe that it is coming normal to ground, almost normal, then afternoon. So they depends. I am skipping these relations because mainly I will focus on the exergy analysis. Now, before coming to this, again the same diagram, conventional flat plate solar collector. Now the construction, first there is an absorber plate. Actually construction may be of different that I am describing here, but the construction which I am discussing is, first there is an absorber plate, then tubes, number of tubes, smaller diameter tubes, diameter about 1 centimeter to 1.5 centimeter, braced or clamped at the back of the tubes, then header tubes. So now you can observe this pump. Actually, this water heater may be natural circulation type or forced circulation type. I have taken forced circulation type. So this pump circulates the water supply through to this bottom header tube. Then water flows through the various these tubes, and finally, after heating, it exits. Now here you can say this L1 is the length of the collector, L2 is width of the collector, W is spacing between two tubes, that is pitch. If we say this is the top view, if we are keeping this flat plate on the ground without any inclination, then let's say this is the top view and this is the front view. Now from front view, you can observe tubes, this hatching portion, that is insulation at the bottom and side, and the glass cover. Purpose of glass cover, all of we know, to reduce the heat loss. Now, again, I am repeating the principle of collection. Solar radiation falling on the glass cover is transmitted from the glass towards absorber. Absorber absorbs. So the solar flux absorbs depends on transmissivity and absorptivity of the cover system, and absorptivity of the absorber plate. Again, I am skipping that, how the transmissivity absorptivity product is calculated. Now the absorbed flux, solar flux is absorbed, temperature of this absorber plate rises. Temperature of absorber plate rises. And now this heat energy, our aim is that this heat energy of the plate should be transferred to the liquid or water flowing through the tubes. Or definitely our aim is to maximize the useful heat gain. But when temperature of this absorber plate increases, the heat loss from this absorber plate to surrounding also increases. And in order to reduce that heat losses from the bottom, we put the insulation at bottom. Side, again we put the insulation at the bottom. And from the top, actually we have to allow the solar radiation, so we put a transparent glass cover. So though we use various means to reduce the heat loss, but there will be heat loss whenever there is temperature difference. So when solar radiation is absorbed by the absorber plate, temperature rises and heat loss also increases. So basically, solar radiation absorbed, transferred, temperature also becomes more, so heat loss also takes place. All these parameters are dependent. For a given solar flux absorbed by the absorber plate, we can say more the solar flux, temperature of absorber plate will also be more. But if we circulate the fluid at higher flow rate, what will happen? Temperature of plate will become less. Means this temperature of the absorber plate, at a first instance, we can say will depend on the amount of solar radiation absorbed by the absorber plate. More absorption, more temperature. But this temperature will also depend on the mass flow rate of the fluid to be circulated. If the flow rate is high, means more heat extraction, means temperature will be less in compared to the when flow rate is less. Second, we can flow the working fluid, liquid or water at different temperature. If we flow it at near ambient temperature, first option. Second, at higher temperature. So if the liquid flows at higher temperature, then the temperature of the plate will be more. Or if temperature of the flowing fluid is less, temperature of the plate will be less. So again, I am repeating, temperature of the plate depends on amount of solar flux as well as mass flow rate of the fluid, temperature of the fluid. Without doing any analysis, logically, we can say the useful heat gain from this device will be mass flow rate of the fluid, Cp of the fluid into del T, mCp del T. Logically, what we can say? mCp del T. And again, logically, we can say that in order to maximize the useful heat gain or to increase the heat gain, loss should be less. So what should be there? Losses to reduce the heat loss, temperature of the absorber plate should be less. If it is near ambient, there will not be any loss. So logically, thinking about by using mCp del T, and second from heat loss consideration, that heat loss depends on TPM. What I can say, energy gain by this solar thermal collector, any solar thermal collector will be more if transport medium or fluid to be heated is circulated at infinite flow rate and at near ambient temperature. At near ambient temperature means circulate the water or other fluid at high flow rate and at low temperature. So in this manner, what we can say, we will extract more heat from the absorber plate. Plate temperature will be nearer to the ambient, so heat loss will also be very, very less. Means heat gain will be more. But what will be the use of this heat energy collected? Of course, we are collecting large amount of heat at a temperature which is nearer to the ambient temperature, because mass flow rate is high, so del T will be very negligible. So again, exit temperature of the fluid is again nearer to the ambient. So there will not be any potential use of such heat energy collected at very or a temperature nearer to the ambient. So we must try to collect, or we should focus on the exergetic value, not only in terms of energy. Just I am giving idea why exergy analysis is relevant to this. Second, if we keep the flow rate high, we know from the chapters of fluid mechanics, pipe flow, that pressure drops, either major energy loss or minor energy losses due to friction or various other fittings, pipe fittings, loss takes place. And energy is required to overcome that heat, that head losses or pressure drops. In case of flat plate collector or any other collector, we use this pump just to keep the circulation or to counter the pressure drops in the tubes. Means we should also consider this pressure drops. Again, I am coming back to my example. 1 kilowatt of electric energy is equivalent to 3 kilowatt of heat energy. If I use this heat energy in a heat pump based system, so 1 kilowatt of electric energy in terms of heat value, it is 3 kilowatt or more. So here pump work in terms of kilowatt, it may be less, but if I convert this in terms of heat value, or you can think in reverse manner, heat energy required to develop that work will be more than this pump work. So we should also include the pump work. That's why this exergy analysis combines both exergy value of heat energy as well as this pump work. So before coming to next page, let me explain how the first law or the energy relations are derived from this for this flat plate collector. Basically, in this conventional flat plate collector, as I have mentioned, this TPM is related to S, mass flow rate, Ti. But all these are combined or some equations are developed. How? For the derivation purpose, just I am giving an overview. We consider the plate portion in between any two consecutive tubes. Consider plate portion in between any two consecutive tubes. Basically, first we calculate the solar radiation coming on a plate portion over the tubes. Over the tube. For a tube, actually there is plate portion. So first we calculate how much heat energy is coming to this plate portion over the tube. And the heat energy is first due to radiation directly falling on the plate portion over the tube. First, radiation falling on the plate portion over the tube. And second, in between any two consecutive tubes, there is a plate portion. Solar radiation absorbed in this plate portion. Temperature of the plate portion rises and this heat of this plate portion in between any two consecutive tubes flows towards plate portion over the tubes. So heat energy over the tube is first directly falling and second conducted from the plate portion in between two tubes. And this derivation is similar to the analysis of fin, rectangular pin fin from the heat transfer. So then finally we calculate the how much heat will be conducted inside the tube, conducted plus convected through the fluid flowing through the tubes. In that manner we can derive the relation, means by using first law analysis. So just I am writing those relations. So just remember the previous figure. The actual heat gain QU by water flowing through, I am assuming water is flowing through the collector, that collector may be calculated by following equation. First, this you see this middle equation, MCP T outlet minus T inlet. There is no need to derivation. M is mass flow rate of water, Cp is specific heat of water, and TO minus Ti outlet and inlet temperatures of water. While this relation, again, there is no first relation. There is no need for heat transfer analysis. Just I am writing the balance. How much is absorbed and minus how much is lost. So useful heat gain is S into AC, where S is the absorbed solar flux per unit area. Solar flux absorbed per unit area, SAC, minus UL. This U is loss coefficient, heat loss coefficient based on this area. Which area? Absorber plate area. So S minus UL, and because heat is lost from plate at temperature TPM, so temperature difference TPM minus TM. So one way to write the useful heat gain is absorbed minus loss. Another is heat gain by the fluid MCP del T. And this third one is obtained by the heat transfer analysis, which I was discussing by considering plate portion in any between two tubes. And that this relation is known as, this equation is Hotel-Villiers equation. And equation is QU is equal to AC. Again, AC is collector area or absorber plate area. FR AC FR S minus UL TI minus TA. Here FR is collector heat removal factor. S I have mentioned solar absorbed flux. UL is overall heat loss coefficient. TI is inlet temperature of the fluid. TA is ambient temperature. Now this collector, actually this derivation of this equation involves the derivation similar to the fin, and second derivation similar to the effectiveness derivation of the heat exchanger. So in heat exchanger also we obtain a relation in terms of NTU. Effectiveness is in terms of number of transfer unit. So this relation, Hotel-Villiers equation, Q is equal to AC FR S minus UL TI minus TA. FR is MCP ULA. MCP upon UA 1 minus this term. In this there is F dash, that is collector efficiency factor, which we write here. I am skipping this, and this collector efficiency factor involves a term phi, and this phi is this. Now from this relation you can think this is similar to the tan hyperbolic ml upon ml, efficiency of the fin, rectangular fin, by using insulated tip fin. Actually in fin we could discuss several cases. Fin loses heat, infinite long fin, or insulated tip fin. And for insulated tip fin, the efficiency we derive tan hyperbolic ml upon ml. So this relation is similar to the fin analysis. That's why you can understand that this formula is obtained by using analysis similar to the fin, and by using this you can say you are also using the steps similar to the steps involved in the heat exchangers. Again, this M is, in case of fin we write it under root HP by Ka. Here again this. Now these are the three relations for heat. Now from this you can say useful heat gain, we can calculate from this, we can calculate from this, or we can calculate from this. Now using the first and third equation, I can calculate mean absorber plate temperature. Actually, I have logically mentioned that TPM, absorber plate temperature, will depend not only S, but it will also depends on heat loss, or it will depend on the mass flow rate, inlet temperature, obviously heat loss. So we can calculate TPM by this relation, which is obtained by combining first and third. And then there is one more definition, that is stagnation temperature. When we study compressible flow, we also define stagnation temperature, but that stagnation temperature is when velocity is reduced to zero, or the conversion of kinetic energy into temperature as well as pressure energy. Here, in case of solar thermal collector, stagnation temperature. Again, you can think logically. If there is no flow through the water heater, then what will happen? Temperature of absorber plate will go on increasing. And at the same time, heat losses will also go on increasing. And in the equilibrium state, when absorbed solar flux is equal to heat loss, the temperature attained is maximum possible. And the temperature attained by the solar thermal collector when there is no flow is termed as stagnation. And this stagnation temperature is this relation again from where? This formula QU is equal to this. Because what we are saying, there is no flow or useful heat gain is 0. So from this first equation, you can get this relation. Actually, now the here, okay, let me proceed. Now the exergy. In solar water heater, if water enters at Ti and leaves at Tu, then in terms of heat gain or energy gain, we say heat gain is mCp del T. But in terms of exergy gain or exergy output by the collector, exergy gain by water is, what will we say? H minus TAS, difference of this, or H2 minus H1 minus TA, S2 minus S1, where 2 and 1 stands for outlet and inlet. So exergy, useful exergy or exergy gain of water is calculated by this. Now here, exergy gain or exergy output of the collector, this is by the water. Now output of the collector means this minus exergetic value of work, pump work. So pump work, if we are giving the pump work, how? Not, why not only WP? Because here I assume that if I am adding WP work, then the same amount of work is converted into heat energy, and that heat energy will also have some exergetic value, that is Q, that is equal to WP 1 minus TA upon Ti. That's why this relation you can see. So pump work, this integral M del P, or from the integral minus VdP relation, the pump work is M del P by rho. So exergy, so heat value is mCp del T, while exergy output is, first exergy gain by water is HO minus HI, that is enthalpy, minus TA SO minus SI, that is exergy gain by the collector neglecting the pump work due to why pump is required? Due to pressure drop, frictional and minor losses. So actual exergy output is this term minus due to pump. The work WP is added, so the exergetic value is this value. Why this value? Because WP plus WP 1 minus TA upon Ti. From that, considering some signs. So from this relation, we can calculate the exergy output. So you can see exergy output is different than energy output. Energy output is mCp del T. That is, this enthalpy difference is mCp del T. While exergy output is this heat gain minus this entropy change. M TA, and this entropy change you can write for incompressible, or this is written here. This useful exergy gain M HO minus HI, this first bracket can be written QU. Why? Because enthalpy difference is Cp del T. Next, MTA. MTA, and this SO minus SI can be written log, in terms of log. Integral dq by t, that is Cp log. So I can write Cp log TO upon Ti. While this Wp by Ti is due to pressure drop. I'm not including air. So just exergy, useful exergy is Qu minus Ta mCp log TO upon Ti. Now, these are the relations which I think I will escape. How the various heat losses are calculated while doing the analysis of the collector. Top loss, bottom loss, side loss. Then we also require the correlation for heat transfer through the tubes, heat transfer coefficient value H, depending on the flow, laminar flow, turbulent flow. Accordingly, we calculate the H and pressure drop or coefficient of friction value. Now, let me come to this conclusion. Hello. Am I audible?
Sir.
Yes, sir.
Let me continue. Now, logically, it is clear that in terms of energy, if we want to increase the energy output of any solar thermal collector, then what we should do? The flow rate of the collecting fluid should be very high. Inlet temperature of the collecting fluid should be nearer to the ambient. And in this manner, useful heat gain will be more. But there will not be any use of this heat energy collected at near ambient temperature. So what our aim should be? To maximize the exergy output considering the pump work due to pressure drops. Pump work required due to pressure drops. Now, if we consider this Hotel-Villiers equation, then useful heat gain from collector can be written as AC F dash S minus UL, and here instead of Ti, in case here, average temperature of the fluid minus Ta. So I am using this simple relation to come to some conclusion, which I have used during my PhD. I have derived these relations. Now, in case of solar thermal collector, flat plate collector especially, in terms of absolute temperature, the difference between TO and Ti is not too much. In between 10 and 11, sorry, in between 273 and 373, difference is 100 degrees centigrade. But in terms of, 0 to 100, difference is 100. Again, 273 to 373, again, difference is 100. But relative terms, difference in terms of Kelvin is less. There is one series that is log 1 plus x. Log 1 plus x can be written as x minus x square by 2 plus x cube by 3. And if it is x is small, then we can write log 1 plus x is equal to x. So by using that series, what I have used, this log TO upon Ti. Because in exergy output relation, HO minus HI minus TA, SO minus SI, SO minus SI, that is entropy change, involves log TO upon Ti. So what I will do, I will replace this log of TO by Ty by this. Twice of TO minus Ti upon TO plus Ti. Why? Because TO upon Ti is less than equal to 2. And I will put this in EXU relation, which I have mentioned earlier, where this relation, either this or this, QU, that is MCP, TO minus Ti minus TA, M, SO minus SI yani means Cp log TO upon Ti. So in that relation, if I put, I will get this relation. Exergy output is this. Using this first one for QU and then MCP TA log TO upon Ti. Exergy output is heat gain minus MCP TA log TO upon Ti, and log TO upon Ti is replaced by this. So on simplification, we get this. Exergy output is this. Actually, I have first, during my PhD, I have performed some simulation and I have obtained some result. And just to give conclusion, I have used such simplified method, or I have derived this relation to come to some concrete conclusion. Now this exergy output from this relation, what we can observe for given S, for given solar radiation intensity absorbed, for given collector area AC means constant. F dash is also nearly constant. But and UL is also constant. Of course, these are variable. Heat loss coefficient will depend on the TPM, will fluctuate. But I am assuming for derivation purpose, let this UL is constant. So keeping other parameter constant, I can say only variable is Ti plus To by 2. Variable is Ti plus To. So differentiating it with respect to Ti plus To. Differentiate and then put it equal to 0, maxima minima procedure. And I have obtained this conclusion that for maximum exergy output, Ti plus To, that is average fluid temperature, arithmetic mean of, not sorry, twice of arithmetic mean, this Ti plus To should be equal to, yeah, you can write in this manner, arithmetic mean is equal to geometric mean of ambient and stagnation temperature. Right? For maximum exergy output, first conclusion is that for maximum exergy output, the average fluid temperature should be equal to geometric mean of under root of, means geometric mean of ambient temperature and stagnation temperature. And by using this critical point, this point of from maximum minimum procedure, put this in M optimum in equation A. Here put, because here Q is equal to also MCP TO minus T, and solve for M. So what I have derived? Optimum outlet average temperature and optimum mass flow rate. And from here, just a minute. Now the conclusions are, from the exergy analysis, conclusions: if the inlet temperature to the collector is nearer to the ambient temperature, then for maximum exergy output. These are conclusion based on this derivation. So if the inlet temperature is nearer to the ambient, for energy output, logically what we have discussed, mass flow rate should be as high as possible. But for maximum exergy output, if Ti is equal to Ta, then mass flow rate must be low, very low. If Ti is, because actually optimum is in bit under root Ta Tst, half of that, sorry, twice. So if Ti is in between ambient and under root Ta Tst, then again mass flow rate must be finite, but twice of its previous value. But if inlet temperature is equal to under root Ta Tst, that is geometric mean of ambient and stagnation temperature, then mass flow rate must be high. M optimum tends to infinity. That is not practical. And this derivation is by ignoring the pump work, pressure drop. And if mass flow rate is, sorry, if the inlet temperature is equal to stagnation temperature, then there will not be any useful heat gain, or exergy output will be 0. There should not be any flow. Now, other than that derivation, if we simulate that collector for various value of absorbed solar flux, so let me explain the procedure first, how the calculation may be done. Suppose I am writing these relation. Now for a given solar absorbed flux S, actually it will vary with the time of the day. So for a particular time or for particular value of solar absorbed flux, what I can do S, and for given ambient temperature, because I have I can assume or I can take the data from any place. So for given ambient temperature, first what will we should do? First assume plate temperature, plate temperature, plate temperature according to the either the ambient temperature or inlet temperature of the fluid. Plate temperature should be chosen more than these two values. And by selecting the plate temperature, now we will proceed to do the various calculations. How? Just say, for example, I have written here. This doesn't require any iteration. I can calculate it first for the given collector, bottom and side loss. But top loss loss will depend on the TPM. Top loss will depend on the TPM. So by assuming TPM, I will calculate the top loss coefficient. Then, as I have assumed TPM, I have calculated top loss coefficient, means now we can calculate the overall loss coefficient. And by using this relation, because we know UL as, this, we have calculated top loss coefficient. This F dash, again I will calculate, then FR, then useful heat gain. Then using this relation useful heat gain, I will calculate again TPM. Start from the assumption of TPM, and then finally again we will calculate the TPM. And for the exact calculation, this final value of TPM must be close to the previous value. So in programming, looping is done or iteration is carried out till the difference of calculated value of TPM and its previous value becomes very, very small. So this is the just idea about the programming. Now the discussion of the results. Now you can see here. I have discussed this. Useful heat gain increases as the mass flow rate increases. The dotted line is for useful heat gain. Useful heat gain increases as the mass flow rate increases. While the solid line is for entropy generation, product of temperature and entropy generation. This also increases with mass flow rate. And basically that exergy output is difference of these two. So exergy output, if I plot the graph exergy upon exergy output and mass flow rate. If you recall the derivation in which I have mentioned, if inlet temperature is nearer to the ambient, the mass flow rate must be finite for maximum exergy output. If the inlet temperature is nearer to the stagnation temperature, then there should not be any mass flow rate, but it is less than stagnation, then mass flow rate must be infinite. So using that two conclusion, again, we can observe we can verify from here also. So this graph is for low inlet temperature. If the inlet temperature is low, the exergy output first increases with mass flow rate. Logically, is it clear? There is no mass flow rate, no useful heat gain, no exergy. So exergy output increases with mass flow rate. And then again, reduces. Means there is some optimum mass flow rate, which we cannot obtain from the energy analysis book, because from the energy analysis there is no optimum mass flow rate. Mass flow rate should be as high as possible, while inlet temperature should be as low as possible. But from this exergy analysis, what we can say, there must be some optimum mass flow rate depending on the inlet temperature for given solar absorbed flux. So this, if the inlet temperature is low, mass flow rate, optimum mass flow rate is in low range. Curve is like this, like a parabolic. Not parabolic, because for higher value of mass flow rate, the exergy value becomes nearly constant. But if the inlet temperature is high, this second graph is when inlet temperature is high, what we can observe, the exergy output increases, though change is very small. But as the mass flow rate increases, exergy output also increases, but the gain will not be too much. So again, what conclusion we can derive, that for maximum exergy output, the mass flow rate should be in low range. I think we are running short of time, so I will not cover. Just I will give another idea. Means by using this exergy analysis for given solar absorbed flux, what we can calculate optimum inlet temperature, optimum mass flow rate, or for a given inlet temperature we can calculate optimum mass flow rate, or for a given mass flow rate we can calculate optimum inlet temperature. And similarly we can calculate for given solar flux what should be the global optimum inlet temperature and global optimum mass flow rate for given solar absorbed flux. Then we can go for entire day, what should be the inlet temperature and what should be mass flow rate. So by using exergy analysis we can decide the range. Now in case of solar water heater, air heater, because it is not feasible for me to discuss all those, just will give you idea. In case of solar air heater, the duct is formed. As I discussed construction, the flow of air also always takes place through the duct. Duct is formed by absorber plate placed as the top and a bottom plate. Flow takes place through the duct passage formed between absorber plate and bottom plate. And if along the flow direction, length is L1, that is the length of the solar collector, and width is L2, and duct depth, let L3 or capital H, whatever you use, then duct aspect ratio is L1 upon L2. L1 upon L2. Just imagine I have to form a rectangle. So the length may be different than its width. So for a solar air heater, suppose I want to have a solar air heater of 100 meter square area, surface area 100 meter square area. One option is choose a collector having length 10 meter, width 10 meter. Length 10 meter, width 10 meter. Another choose length 20 meter, width 5 meter. What I am doing? L1 into L2 is equal to area. So if I go on reducing the width, I have to increase the length. Means the aspect ratio for the duct, which is defined as length to the width, if it increases, then what we are going to do, we are manufacturing longer collector, or a collector having high aspect ratio, means width becomes less. Width become less, it means cross-sectional area of the flow through the duct. Cross-sectional area of flow means width into depth. So by using by increasing the aspect ratio, we reduce the width, means we reduce the cross-sectional area. And for the given mass flow rate through the collector, what will happen? The velocity of flow through the air meter will increase. Velocity of flow through the duct or air meter will increase. And as the velocity increase, heat transfer coefficient as well as pressure drop, both increase. Heat transfer will increase, means efficiency, collection efficiency of solar air heater will increase. Pressure drop increase, means the power required for the pump or blower will also increase. So several researchers based on this logic have suggested, there are so many publication of even the IIT pupils, that to improve the energy efficiency of solar air heater, we should use collector having large aspect ratio, or collection efficiency increases as aspect ratio increases, means manufacture a slender collector, or fabricate, instead of a large collector, use a smaller number of collectors connected in series. For the same total area, use different number of sub collectors connected in series. Same logic, velocity increases, heat transfer will increase, efficiency will increase. But if we connect, or if we use various sub collectors in series, or if we use higher aspect ratio, definitely velocity will increase, heat transfer will increase, collection efficiency will also increase. But at the same time, pressure drop or pumping power will also increase. And this pumping power, just remember 4 FLV square upon 2 GD, pressure drop equation is squarely proportional to the V square, pressure drop, head loss. Means power required to pump increases as a power law with mass flow rate. So if we perform the exergy analysis, means if we consider this work, then we will observe that it is not right to use high aspect ratio collector or use number of sub collectors in series for higher mass flow rate. Actually, we can use if the mass flow rate is very, very small. So just I am giving idea that based on exergy analysis, the result obtained will be different than energy analysis, because based on the energy analysis alone, what will say? Use smaller collectors connected in series. One more example I will give. In case of solar air heater, because air is not having suitable thermophysical property, in order to improve the performance, what we can use? We can use fin or extended surface at the bottom of the absorber plate, or we can use artificially roughened surfaces on the bottom of the absorber plate. Now just to understand, assume a plate, absorber plate, top is painted black, while at the back side use an expanded metal mesh, net, mosquito net, metallic mosquito net, adhere that to the plate. Then that rough element is roughness element on the absorber plate. Similar to that, we can attach wires. We can create artificial roughness by some other means. So by using artificial roughness on absorber plate, for example, this expanded metal mesh, what will happen? It will act as a turbulence creator. And as the flow of air is mostly turbulent, so in turbulent flow, there is laminar sublayer, boundary layer. So this artificial roughness geometries break that layer or create the turbulence or enhance the heat transfer coefficient. And again, enhancement of heat transfer coefficient always comes by the expense of pressure drop. So by using this artificial roughness geometry, definitely heat gain will increase. And several researchers have developed the correlation for heat transfer coefficient and friction factor for these roughness geometries, but just by varying. But someone has used this expanded metal mesh, or initially starting from, imagine here, if you see my diagram, just a wire placed like this, various wires on the plates, simple wires glued to the absorber plate. Then keep the wires inclined. Next provision. Then instead of circular wire, use a rectangular rib. Then that rib can be chamfered. So there are so many provisions to create the or use the artificial roughness geometry. And they have given the conclusion that we should use the artificial roughness geometries. And again, because there will be more pressure drop, so you can use the exergy analysis to determine the optimum size of the roughness geometry. That is even for only for lower flow rate, because for higher flow rate, pressure drop will be very much, and from the exergetic point of view, these roughness geometry will not be suitable. Now I should finish now. Thank you. If anybody wants to ask question, any query, you can ask question. Siva Reddy, Dr. Siva Reddy. Because now time, because I have been asked to continue up to 12:30. So if anybody has query, am I audible?
Yeah, sir. So dear participants, please unmute yourself and ask any or interact with Professor Gupta sir.
I think now session is open for question. From root level, we start explanation of exergetic analysis.
Participants, please unmute yourself and you can interact with the professor.
Either me or Dr. Siva Reddy is also expert in exergy analysis.
Yeah.
Later on, participant may contact. Because we have done under the same guide, PhD. Okay. I think there is no question. Are the participants from mechanical background or other background also?
Mechanical and also other branches also, sir.
Majority mechanical, sir.
Mechanical, triple E.
Mainly mechanical. Oh.
Triple E, physics.
Oh, okay. Chalo. So Siva, should I finish?
Yes, sir. Coordinator, sir. Sir.
Sir.
We will close.
Participants, any questions? So as we are not receiving any queries from the participants, so we are going to conclude. So thank you, Manoj Kumar Gupta sir, for accepting our invitation. So to give an expert talk on thermodynamic analysis of solar thermal collectors.
Thank you to Dr. Siva Reddy for inviting me.
Yeah. Siva Reddy is invited. Okay, thank you, sir. Once again,
test book is there. Power query.
Okay.
You can see the SAR test book. It is in Amazon also. It is available.
This book is only for UG purpose, undergraduate.
Yes, sir. Yes, sir. Yes, sir.
So sir has given a lot of information regarding exergy analysis. So hope the participants may gain the knowledge in this area. So thank you, sir, once again. And I sent one email to you. So you go through that and send, sir.
Okay.
So thank you, sir. Sivad, sir, if you want to speak.
Thank you very much, sir.
Thank you, और Siva. Can we chat
Yes,
here
sir.
for some time?
बढ़िया हो गया, sir.
There, okay. ठीक है,
I will call you, sir. Evening, I will
Okay.
call you.
Yeah, evening I will call you. ठीक.
Okay. Oh.
Thank you, sir. Thank you, HOD, sir.
Thank you, sir.
Thank you. Munmun?
So dear participants, so this is the morning session. Next in the afternoon session, so we have the topic on solar heating, steam generation and space heating applications by Dr. K.V. Sharma sir, Professor of Mechanical Engineering, JIT Hyderabad. So all of you join at 2 p.m.